Hello, I welcome you all to this class. In this class, we are going to start the gas turbine. So gas turbine is what? The gas turbine is like a turbine only, which is used to generate the power. How it will generate the power? That when the pressurized air is used to spin the turbine. So whenever the turbine is rotates, right, it generates the powers. So that power is used in various applications. So various applications of gas turbine is what? That gas turbine power is used in aircraft, right, in electrical generators, in ships, marine, etc. Now first of all we'll see that what are the main component in any gas turbine. So basically the gas turbine is having only means three main components, right? That is compressor, combustor and turbine. Additionally, we can use the heat exchanger also, which means if you have a gas turbine is a closed type, right? So compressor is used to compress the air. In combustor, the combustion will takes place, and in turbine the expansion will takes place. Before going to in detail, we'll see the how many types of gas turbine we have. So gas turbine means on basis of the cycle we can divide the gas turbine is of two types. That means that you can say types of gas turbine cycle. That GT means gas turbine cycle. So basically two types of gas turbine cycle we will define. That is open cycle, right, and the second one we have a closed cycle. Open cycle and second one is the closed cycle. Now on behalf of the combustor means that you have to supply the heat to the combustion in combustion chamber, right? So for heat we need combustion. So combustion will take place either by keeping pressure constant or by keeping volume constant. So further you can say that gas turbine is of two types, that is either it will be the constant pressure or constant volume. So here only you can write that is that constant pressure and second one is the constant volume, right? But in general you need to remember that gas turbine cycle is of two type, that open cycle gas turbine and the closed cycle gas turbine. But most of the cases we will use only the constant pressure gas turbine cycle. Either it is the open or closed, means the heat we will supply in combustion chamber by keeping pressure constant. Rarely we are using the combustion chamber in which we are supplying the heat by keeping volume constant. So now we will look at that what are the construction, means what are the main part of a gas turbine cycle. So as you know that in any gas turbine cycle mainly three main components, that is compressor, combustion chamber and the turbine. So let's see that a schematic diagram of a gas turbine cycle. So here we'll go very carefully that this is your air compressor, right, and here we have a combustor, means in which the combustion will takes place, and another component is a turbine, right, that is gas turbine basically. Okay, now so first of all what will happen, the air will enter into the compressor from the surrounding, right? So this is the inlet of the compressor and this will be the exit of the compressor. So first you can arrange this, let's say these are the arrangement. So this is the inlet of the turbine and this will be the exit of the turbine. Okay, now so first of all that here you can say the air into the compressor, and whatever the air is entering into the compressor, that air is atmospheric air, means the pressure temperature will be the atmospheric pressure and atmospheric temperature. So first let's say this is the 1, that is inlet, we assume it is the 1. So at this 1 the air is entering into the compressor, this is compressor, So how the compression will take place? The thermodynamic process which follows here, that is the reversible adiabatic compression. So reversible adiabatic compression means the entropy will be constant, right? That entropy will be constant. After compression, the pressure and temperature will rise. So it will reaches to the state 2, right? So here the pressure is become P2 and temperature is T2. And here the pressure and temperature is P1 and T1. Now in combustion chamber, you have a combustion is takes place. So it means that we are supplying the heat. So Q you are supplying. How the process is executed in combustion is by keeping pressure constant. So we are not disturbing the pressure while we are adding the heat. So when you add the heat, it means that the pressure will remain constant but the temperature will rise. So at the point 3, when the gases is leaving the combustion chamber, it become hot gases. So now you can say it is a hot gases. So hot gases has pressure will be P2 itself. Why? Because P2 and P3 will be same. This is the state 3, but the pressure will be constant, that is same, and the temperature is become T3. This T3 is the maximum temperature throughout the cycle, right? So further the hot gases will enter into the turbine. So when this hot gases is entering into the turbine is having shaft, and on the shaft the blade is mounted. So when the hot gases is strike, that hot gases is not a normal gas, it's having pressure is maximum and the temperature is maximum. So you can say the high pressure high temperature gas, when a strike over the turbine blade, so there is a thrust will create, means because of that pressure the blade is a start, means shaft is a start spinning, and because of that spinning of the shaft the work has developed. So first of all, whatever the work is produced, first will supply the work to the compressor, right? So that's why we have to couple the turbine and compressor. So first, when the work is produced in the turbine, some work has to supply to the compressor to run the machine, and whatever the work is remain after supplying to the compressor, that work is utilized for power production. Means if you are using the gas turbine to power the aircraft, so that work is used to give the power to the aircraft, or if you are using the gas turbine for electrical generation, that work is used for the electrical generator, right? And so on. So here whatever the work is remain, that work we call it as a turbine work, okay? And this work is a power output, right? And after expansion, that is pressure and temperature further will fall down, and the pressure and temperature will become here, that is a state 4. The pressure and temperature will be P4 and T4. This pressure temperature is less than this value. Now as it is the open cycle gas turbine, so after expansion of the gases, we will release the gases, means exhaust gases, to the open atmosphere. If it is the closed cycle gas turbine, so what we need to do, that we have to send these gases back to the compressor. So but before sending it, here you have to use the heat exchanger. That is the case of the closed cycle gas turbine. So this is what the working principle of any open cycle gas turbine, which works on the constant pressure cycle. Now this whole scenarios we will see on the TS diagram, that is temperature and entropy diagram. So let's see that. We are drawing here. Just wait. Yes. So you can draw. Yes. You can draw the temperature and entropy diagram. So this is temperature we are taking on y-axis, and entropy on the x-axis, right? So this is the entropy. Now the two constant pressure line we have to draw. That first you have this is the high pressure line, right? This is the high pressure line, and this will be the low pressure line, right? Now so now first of all what we are doing, that in 1 to 2, if you look at here, 1 to 2 is the reversible adiabatic compression, 2 to 3 is the constant pressure heat supplied, and 3 to 4 is the adiabatic expansion. So it is the constant open cycle gas turbine. So 4 to 1 will won't return back, right? Why? Because from 4 itself we have to release the gases to the open atmosphere. So first of all, you can see this is the high pressure line, that is maximum pressure throughout the cycle, and is the minimum pressure. Now first of all, adiabatic compression, reversible adiabatic compression means it is an ideal case, right? So 1 to 2 you have a constant, means entropy will be constant. So let's say this is 1 and this is the 2. 2 to 3 you are supplying the heat in combustion chamber by keeping pressure constant. So this is the constant pressure line. And 3 to 4, that is expansion in a turbine, right? Now so you can show this by arrow, up compression and expansion, and this is what you have. So here we won't send it, so we won't show any arrow mark, right? Now that is the ideal cases. If isentropic means if it is the actual, for actual process you can show this by, yes, so for actual process this will be the, this is means entropy will not constant 1 to 2 dash, and this will be the 3 to 4 dash, and this is 4, right? So here you have this is the temperature versus entropy diagram for the open cycle constant pressure gas turbine. Now we will see that every cycle you learn in your previous classes, that Otto cycle, diesel cycle, so each cycle is following some thermodynamics cycle. So this gas turbine works on the cycle, that cycle we call it as a Brayton cycle. The Brayton cycle is also known as the Joule cycle. So first of all, that Brayton cycle actually it is the closed cycle gas turbine power plant, right? So closed cycle gas turbine means what? That exhaust gases is not released into the open atmosphere, but it will be sent back to the compressor, right? By cooling the temperature and then, right now. So now first of all we will see the, you can write, just wait, yes. So now you can see here that Brayton cycle means, that is, just wait, Brayton cycle, okay. So Brayton cycle is also known as the Joule cycle, right? Joule cycle. So your gas turbine plant works on the Brayton cycle. So we can make a note that GT cycle works on Brayton cycle, right? Works on Brayton cycle. So Brayton cycle means what? It is also having 4 process, that adiabatic compression and expansion, and constant pressure heat supplied, as well as constant pressure heat rejection, right? So you can say that it has 4 process, right? And what are those? First you can say the reversible adiabatic what? Compression, okay, adiabatic compression. Second one is what? That is reversible, after compression you have to add the heat, means heat supplied at constant pressure, right? At constant pressure. Next, after adding the heat, we have to expand the gas. So you can say that further reversible adiabatic expansion, that will be in the turbine, right? And then finally you have to heat rejected at constant pressure, that will be in the heat exchanger, okay. So these are the 4 processes. Now if we draw this process on the PV diagram as well as on TS diagram, so how it looks like, see first. So first of all we will discuss this on PV diagram right now. So here you can see this is what you have, a pressure, okay, and this is the volume. So pressure we are taking on on your y-axis and the volume will take on x-axis, right? So first you have a compression is takes place adiabatically. So adiabatically compression will be like this, that is, let's say it is 1, right, and this is the 2. After compression you have to add the heat where in your combustion chamber by keeping pressure constant. So let's say this is 2 to 3 and finally 3 to 4 is the adiabatic expansion, and this is what 4 to 1. Further you have a heat is rejected at constant pressure. So this is 3 to 4. So here you can show this 1 to 2 is the compression in your compressor itself, 2 to 3 combustion chamber, that is heat supplied at constant pressure, 3 to 4 adiabatic expansion, it is turbine, and 4 to 1 that heat is rejected in heat exchanger. Alright, now so here you can mention that P is equal to constant and this is also P is equal to constant. Here adiabatic process, it means that the law which govern that PV to the power gamma is constant. Okay, so it looks like a Z, actually it is 1. Right now if I see this Brayton cycle on TS diagram, that is temperature versus entropy diagram, then how it will be, that it is same like just we have drawn. So again I'll show you that this is temperature and this is the entropy. Okay, so two pressure line we have to draw. This is high pressure line and this is the low pressure line. So first you have a 1 to 2, this is the adiabatic compression, right? 2 to 3 heat supplied at constant pressure, 3 to 4 expansion in a turbine, and 4 to 1 you have a heat rejection, right? So this is your compression, it is expansion, and this is heat supplied at constant pressure, and this is heat rejection at constant pressure. So this here you can say this is the maximum pressure line, right? That is P2 is equal to P3 on this, and in this P4 is equal to P1. So if you look at the maximum temperature of the cycle is T3, and this is the inlet of the turbine. So at the inlet of the turbine, the temperature will be the maximum throughout the cycle, that you have to remember. Okay, next, then we need to see that what is the efficiency of a Brayton cycle. So efficiency of anything, you know that output by input. Output is what? Work done, and input is what? Heat supplied, right? So work done actually we will see in terms of the heat supplied minus heat rejection, right? That is means thermodynamics principle is that only, that when you give the heat to the system does work. And also you know the second of thermodynamics, that all the heat cannot be converted into work. If the all heat is converted into work without heat rejection, that machine is not exist, and that machine is, we call it as a perpetual motion machine of kind 2, means that is the hypothetical machine and which will not exist in a real world, right? So for that always you remember that heat rejection will be always high. So you can see this line, this is maximum as compared to the, this means if you compare the length of this 4 to 1 and 2 to 3, 4 to 1 is always more than the 2 to 3, right? Now then we will see the efficiency of Brayton cycle. So its continuation you can write that efficiency is nothing but your performance of the Brayton cycle, right? Efficiency of Brayton cycle. All right, okay, so efficiency of Brayton cycle. So efficiency you are denoting that neta. So neta Brayton, you can say neta Brayton is equal to output by input. All right, output is what? Output is nothing but the work done, and input is the heat supplied. Further you can write that neta Brayton is equal to heat supplied minus heat rejection by heat supplied. Is it or not? So if you look at heat supplied will get cancelled, means 1 minus heat rejection by heat supplied. Sorry, it is the heat supplied. Now we will see that what is the magnitude of heat rejection and heat supplied. So for that you can refer the figure, just a second. Yes, right. So I'll show you that in PV diagram itself or TS diagram. Here you are adding the heat from what? 2 to 3, and here you are rejecting the heat. So heat rejection and heat supplied and heat rejection at constant pressure, and heat formula you know that mcdt, right? So if you are adding or rejecting the heat by keeping pressure constant, that means the equation will become mcp dt, right? So now directly I am writing that. I hope that you know about the basics of thermodynamics. If you don't know, you can go through with the videos that reviews of thermodynamics, right? So we can see here that, sorry, yes, yes. So now you can say that heat supplied, HS means heat supplied, is what? mcp, and you are supplying the heat from 2 to 3, and T3 is the maximum, so you can say T3 minus T2, out final minus initial. And heat rejection is what? That heat rejection is mcp, okay, and this is what? T1 minus T4, sorry, T4 minus T1, high minus low. Heat rejection will be negative, right? So that's why it will become like this right now. So mcp T4 minus T1. If I substitute these two value into this equation which we have generated here, 1 minus heat rejection by heat supplied, so your efficiency of Brayton will become like this, that efficiency of Brayton is equal to what? 1 minus heat rejection by heat supplied. So heat rejection is what? mcp T4 minus T1 over mcp T3 minus T2. If you see m and CP will get cancelled, the equation will got, that is efficiency of Brayton is equal to 1 minus T4 minus T1 over T3 minus T2. Okay, let's say this equation as a 1, right? Now next what we need to do, we have to find out the relation between temperature and pressure. Why? Because if you see the whole Brayton cycle or gas turbine cycle is totally depends on the pressure ratio only, is it or not? Why pressure ratio? Why? Because that efficiency or performance of your gas turbine will decide by that how much heat you have added, or you can say that how the compressor has compressed the air, right? If the compressor has compressed the air at a maximum point, it means that the performance or work done by the turbine will be maximum. So if the work done by the turbine will be maximum, it means that the plant will give you the better efficiency. Okay, so now you can say that we'll generate the relation in temperature and pressure. So first of all, I'll come to the 1 to 2 process. Look at here that 1 to 2 is the adiabatic compression. You know the thermodynamic relation that you can say 1 to 2 process, right? So what is the temperature pressure relation? T2 by T1 is equal to P2 by P1 whole power gamma minus 1 by gamma. Okay, that is gamma is the adiabatic constant. If for air, the gamma will be 1.4. Now, so you can say P2 by P1 is a pressure ratio actually. So here itself we can say that T2 by T1 is equal to Rp to the power of gamma minus 1 by gamma. Rp is nothing but the P2 by P1. Rp is P2 by P1, right? So you can say T2 is equal to T1 times of Rp to the power gamma minus 1 by gamma. Okay, now let's say this as it is. Now further we'll come to the expansion, means in turbine side. So we can say 3 to 4 process. So 3 to 4 process means what? That T3 by T4 is equal to P3, okay, P3 by P4 to the power of gamma minus 1 by gamma. So if you look at here, that we see that P3 is equal to P2 and P4 is equal to P1. Why? Because these are the constant pressure process, right? So this equation further leads, that is P3 is P2 and P4 is P1 whole power gamma minus 1 by gamma. Okay, now so if you again that is P2 by P1 is Rp to the power gamma minus 1 by gamma, it means that these two sides are equal. It means, so on behalf of that you can say that T2 by T1 is equal to T3 by T4. Alright, it means that, see here, that in this equation 1 to 2 process, T2 by T1 is Rp to the power gamma minus 1 by gamma, and in 3 to 4 also, that T3 by T4 is equal to Rp to the power gamma minus 1 by gamma. So it means that as the RHS is same, so the LHS will also same. Now further, you know the efficiency of Brayton is what? Okay, so efficiency of Brayton we already written, that equation 1. So you can say from equation 1, efficiency of Brayton is what? 1 minus T4 minus T1 by T3 minus T2. Is it? Okay. So if I do some simplification, let's take the T1 as a common from the above equation. So 1 minus T1, it will become T4 by T1 minus 1 by, in this if I take common as a T2, right? So it will become T3 by T2, sorry, it will become T3 by T2. I am taking T2 as a common, and this is minus 1. Further, if you look at and if you observe very carefully, that here once you cross multiply, that means T2 T1 is equal to T3 T4. Alright, that leads T3 by T2 is equal to, yes, T3 by T3 minus T2. Yes, so it will become, wait, so that is T3 by T2 is equal to T4 by T1. Sorry, T2 T4 is equal to T3 T1. Here is a mistake right now. So cross multiply, you cross multiply T2 into T4 is equal to T3 into T1. So T3, we need to find T3 by T2. So when the T2 will come in the denominator, T1 will goes here, right? So this will leads you that T4 by T1 is equal to T3 by T2. Understood? Just cross multiply and rearrange this term. So when you rearrange, T3 by T2 is equal to T4 by T1. It means this term and this term will get cancelled. So equation is what? That Brayton is 1 minus T1 by T2. But T1 by T2 is what? T1 by T2 is nothing but your, we can say T2 by T1 is Rp to the power gamma minus 1 by gamma. You can see here T2 by T1 is Rp to the power gamma minus 1 by gamma, which means T1 by T2 is 1 by Rp. Just reverse. So here the efficiency of Brayton, finally we can say that efficiency of Brayton is equal to 1 minus 1 by Rp whole power gamma minus 1 by gamma. Okay, so this is how we will find out the efficiency of a Brayton cycle. So this equation will says that at a high pressure ratio, the efficiency of a cycle will be high, right? So this is all about the gas turbine cycle. In next class, we will discuss some numerical problems and we see the method to improve the performance of a gas turbine cycle. Thank you.